Example 8. Find the velocity and position functions of a body falling freely from a height of 0 meters under each of the following sets of conditions. So the idea here is that some rock or something is falling freely, which means it's dropped, from a height of 0 meters. That means that we're starting from 0 and we're going to increase or decrease our height as it falls. So the acceleration for part A is 9.8 meters per second as the body falls from rest. That means, for example, I hold the object in my hand and I let go of it. The second scenario is that the acceleration is also 9.8 meters per second squared, and the body is propelled downward with an initial velocity of 1 meter per second. What this means is that I throw it, or I push it down, or it has a jet, or something that makes it have a velocity the second it starts. So the idea behind this is very similar to the last one. We're going to use our knowledge of antiderivatives in order to evaluate this. So let's start with part A. Falling from rest. So what we know is that when it falls from rest, we're starting without moving. So this is when t equals 0, the velocity is also 0. This means that v of 0 is equal to 0. This is important to point out because in the next problem this won't be the case. So let's start with acceleration. Acceleration is 9.8 meters per second squared. So what we need to do then is find velocity. Well, we know that the derivative of velocity is acceleration, so the antiderivative of acceleration would be velocity. So what do you have to take the derivative of to get 9.8? Well, as we saw with the antiderivative, in order to get 9.8, you need to take the derivative of 9.8t. But remember, whenever you take an antiderivative, you're always going to get this extra c value. And this is because d dt of 9.8t plus c is equal to 9.8 because c is a constant, so it goes away. Now we're going to use our initial value, v of 0 equals 0. So 0 is equal to, when I evaluate when t is equal to 0, then you get 0 is equal to c, and then you just plug it back in for c to find a velocity function. So we get v of t is equal to 9.8 t. There's our velocity function. But now I want to be able to find the position function. So in order to find the position function, I need to remember how position and velocity are related. So s of t is position, and s prime of t is velocity. So if you want to go backwards, we need to take the antiderivative. So v of t is 9.8t. So s of t then is 9.8t squared divided by 2. Because we add the exponent, we add 1 to the exponent, and we divide by whatever this number is. So this is going to be 4.9 t squared plus c. Well, if we haven't started moving when t is 0, s of 0 is also 0 because we haven't moved yet. So we set the whole thing equal to 0. 4.90 squared plus c, and you get c is also 0. So then your position formula, s of t, is just 4.9 t squared. And that's it. We found our position formula right here, our velocity formula, and we found our position formula. Now for part B. This one's a little trickier. What I want you to do is try it on your own. I'm going to get it set up, and then I'll let you guys go. So this is the part where we're propelled downwards. So in this example, we're still starting from an initial position, but since the object is being propelled downward, it has a initial velocity of 1 because it's being propelled downward at 1 meter per second. So right when it launches right away, it's at 1 meter per second. So we're going to follow the same idea. We're going to take a of t, which is 9.8 meters per second squared, and we're going to determine the velocity by taking the antiderivative. So you get 9.8 t plus c, but this case, v of 0 is equal to 1. So 1 is equal to 9.8 times 0 plus c. So you get that c is equal to 1. So our velocity function is 9.8 t plus 1. Now what we need to do is we need to find our position formula. Well, we have v of t is 9.8 t plus 1. So s of t is 9.8 t squared divided by 2 plus t plus c. This is because the antiderivative of a constant is just t. So we get s of t is 4.9 t squared plus t plus c. Well, we know our initial position, s of 0, is equal to 0. So we set the whole thing equal to 0, and we plug in 0 for every t value. So c here is 0. And I want to point out this c is different than this c. So I'm going to write a subscript of c sub 1 just to alleviate any confusion. So our position formula then is 4.9 t squared plus t. And that's it. That's all there is to it for finding initial value problems. Again, the AP test loves these, so let's make sure we know how to do this.